So did you experience your first real bore event? Tomorrow's going to be worse.
Oh man. Wow.
Tomorrow's going to be worse.
There's worse coming?
Tomorrow's going to be fun.
It's going to be fun.
Tomorrow's going to be fun.
It will be my normal day.
Bora is the wind.
Yes.
Did you notice some winds during the past 2 days? No? Did you go outside in the past 48 hours?
That's why.
Yes, I can hear.
You didn't notice some strong, steady wind, northeast direction? You're joking?
No?
No? Okay. Well, somebody who's not affected by it. Seriously, you didn't notice strong wind?
June will be outside tomorrow 24 hours.
Tomorrow?
Yeah. 24 hours be outside.
Tomorrow?
Tomorrow's going to be worse. Well, you're not going to notice it. No problem. So, let's remember what we did the last time. We looked at the conservation of momentum. Okay? So we start with the continuity equation, and then we ask ourselves what are the forces acting on the element of fluid. So there can be two kinds of forces acting on the element of fluid. One is body forces. Those are the forces without physical contact. Okay? And they exist because the medium is in a force field. So we just looked at the gravitational field, but it could be any other kind of force field, electromagnetic or whatever. And then the second kind of forces that we looked at was surface forces. Okay? And so they are exerted on an area element of the element fluid, and they can have two components, a normal component and a tangential component. So we looked at the conservation of momentum, starting from the Newton's law of motion. Okay, first we looked at this tensor for the shear stresses on an element of fluid. Okay, and so our Newton's law of motion, mass times acceleration, is equal to forces on the right hand side. A body force that we denote by F, could be any force, body force, and a stress tau, which is all the surface forces acting on the element of fluid. Okay, and the stress tensor tau is related to the deformation field. We know that the rotation field doesn't deform the element, and it doesn't accelerate the element. Only the strain weight tensor E can accelerate the element. And this is the what we call the Cauchy equation. Okay? So the basic equation for the conservation of momentum. Now we said, okay, how can we progress on that stress tensor tau? We use the constitutive equation for Newtonian fields. So a constitutive equation is a relation between the stress, surface stress, and the deformation of your continuum. You can have a constitutive equation for any continuum, even for solids, but obviously we're going to do it for fluids. So you start from the condition of fluid at rest, so you only have normal forces or stresses acting on the element of fluid, and that's pressure. Okay? Because there's only normal forces, we know that the stress tensor is isotropic, so that's the same value everywhere. And the only second order isotropic tensor is the Kronecker diagram. So any isotropic tensor tau in static condition has to be proportional to delta. So in static condition we use that tau equal to minus P pressure times the Kronecker diagram. Okay? But that's just in static condition. In a moving fluid, then you have stresses, shear stresses, and there must be a dependence on the viscosity. We looked at this in the very first lecture. Right? And those are the diagonal terms of the stress tensor tau. And we call it sigma. Okay, that's going to be the tensor for the dynamical part of the stress tensor. And that sigma is what we call the deviatoric stress tensor. It's not isotropic, obviously. The isotropic part is the static component. And that as deviatoric stress tensor is related to the velocity gradient tensor, which we have seen already. Okay? And so that velocity gradient tensor has two components, we know. E, which is the symmetric part, and R, which is the one related to the rotation. Okay? Yes.
And then the rotation part have a half.
Sorry?
Shouldn't it, like equation H, shouldn't it be E plus a half R?
Probably. Yes, it was half of the rotation tensor, right? Yes. Anyway, we're not going to care about the rotation tensor. So the rotation tensor is antisymmetric. The symmetric part is the E tensor. And so because it's antisymmetric, it doesn't generate any stress in the fluid. It only rotates the fluid potentially, but it doesn't generate any stress, and so it doesn't generate any acceleration. And so all the stresses are generated by the strain rate tensor E, which is that. Okay? So we can just ignore the rotation tensor. So whatever sigma deviatoric stress tensor that we have, that is going to be proportional to the velocity gradient tensor. And the only part of the velocity gradient tensor that we care about is the strain rate tensor E. Now is where you make a lot of assumptions and approximations. Okay? We make the hypothesis of Newtonian fluid, so that there's a linear relationship between the stress and the deformation, and the viscosities are constant. So you reduce the number of components of that tensor, fourth order tensor. Then you say that the medium is isotropic, the deviatoric stress tensor is symmetric, and then you use the Stokes hypothesis for pressure. And eventually you get to that. Okay? So your constitutive equation for Newtonian fluid, under all those assumptions, has that simple form 21. Okay? So you have a part which is the static component, minus P chronic delta, and then two components which are related to the viscosity. Okay?
Sir?
Yeah.
Professor, please can you go back to the assumptions slides? That slide, yeah, no, that one. Says that the hypothesis of isotropic medium lifted from 81 coefficients to just 3. How was it 81 coefficients?
When you start from a fourth order tensor, kappa, okay, ij, mn, that has 81 components. Okay. So it's not very tractable, 81 components. Okay. Second order tensor has 9, fourth order tensor has 81. So you want to reduce the complexity of that tensor. So you make a bunch of assumptions. You can read a book if you're interested on exactly the steps, but it's not very interesting for us. Yeah. And so now you take that constitutive equation for Newtonian fluids and you plug it into the Cauchy equation for motion. And you end up to what we call the Navier-Stokes equations. Okay. So you start from the Cauchy equation, you use the constitutive equation, and after a few steps, you end up with this expression for the conservation of momentum. Which I think is, well, then you make the assumption of incompressibility, so that divergence term is equal to 0. And so you're just left with this equation of momentum. So your mass times your acceleration is equal to a body force, and then your pressure gradient, and any stress on the surface, or whatever you want those stresses to be. Okay? Obviously, if you neglect viscous effects, which is a good approximation somewhere in geophysical fluids, then you're left with the Euler equation. Okay? So your accelerations will be balanced by a pressure gradient and a body force, which is the gravitational force, which has only has only one component in the vertical. Then we are not going to introduce another kind of body force because you'll see this in the second part. So I'll just skip this. Okay, just keep in mind that whenever during the second part you will be introduced to the Coriolis acceleration or the Coriolis apparent force or whatever you want to call it. That apparent force or acceleration is something that goes into those body forces. Okay, so suddenly you don't only have one body force, the gravitational force, but you have two body forces. One is gravitation and the other one is the Coriolis acceleration or apparent force. Okay? And that will deviate or accelerate the fluid flow. Okay. Okay, so, well, I'll give you this. I've created that Dropbox folder, so all the slides are there, and I'll send you an invitation. Maybe, no, I didn't do it yet, so I'll send you an invitation this afternoon. So if you want, you can, well, whenever they will explain you the Coriolis acceleration, you can look back at these 3-4 slides. Okay, there's a bit of derivation on how you obtain all the different components of the Coriolis force. So eventually, when you use the Coriolis force or the Coriolis acceleration, you end up with a depending on how you want to call it. There's people who like to call it a force, and so they put it on the right-hand side. And some other people, they like to call it an acceleration, and so they put it on the left-hand side together with the Lagrangian derivative. So you have the Lagrangian derivative of your flow and the acceleration due to Coriolis, that FU/FV. And that equal to all the forces on the right-hand side. So if you neglect viscous effect, the last terms on the right, then you have a balance between two forces mainly. One is the Coriolis force on one side and the other one is the pressure gradients. So those two forces, the balance between those two forces, the Coriolis and the pressure gradient, will determine your velocity field U and V. Okay? And that is basically the winds that you see when you look at the weather map, all those lines of constant pressure. Those lines of constant pressure, they give you a pressure gradient, and that pressure gradient is balanced by the Coriolis force. And the result is a wind, in that case, U and V, which is in balance between the pressure gradient and the Coriolis force. So whenever you see a pressure gradient in a map of weather, for example, and you know if you're in the northern hemisphere or in the southern hemisphere, then you know exactly where the wind is going, because you know that the main balance in that flow away from boundaries, so you can neglect the viscous effects. The main balance is between the pressure gradient and the Coriolis acceleration. So you know what kind of structure U and V has. Okay, so now we have those two conservations. We have continuity at the bottom, and we have the momentum equations and the conservation of momentum for the fluid flow. So now we're going to do the energy, or almost all of the energy part. Okay, so we're going to look at the conservation of energy in a fluid, and so we're going to look at the rate of change of my mechanical energy, so the kinetic energy plus the potential energy. And then next time we'll introduce the internal energy, the first law of thermodynamics, which you probably have seen in thermodynamics. And then we'll make an example of the conservation of energy, which is very useful, which is called the Bernoulli equation. Okay? But we'll start with the rate of change of the total energy. So we just define potential energy as mass times the gravitational force times h, whatever height your fluid is. And then the kinetic energy per unit mass is half of rho u squared. Okay? And so we'll derive the conservation of mechanical energy as usual. We're talking about fluids, so we're going to look at the rate of change in our energy. So we're going to look at the rate of change in mechanical energy, and that is going to be equal to the rate of change in energy for whatever reasons, plus the rate of work done on the element of fluid. Okay, there could be shear stresses, there could be compression, there could be many things. minus the rate of viscous dissipation. Okay, and that is always going to be negative because whenever there's viscous dissipation, you lose kinetic energy. Okay, so we're going to derive an equation that states what is the rate of change of total mechanical energy, and that is going to be equal to all the rate of works done on the element of fluid minus the viscous dissipation on the element. Okay, so first we're going to look at just the kinetic energy, and then we're going to add the potential energy. And we're simply going to do that by taking the momentum equation, the Cauchy equation, and do a scalar product with the velocity vector. Okay, so the Cauchy equation in this form, Ij xj, for the three components. And we're just going to do a scalar product of this with the velocity vector and get to an expression for the kinetic energy. Okay, that I show then. So just for the x component, you expand this du by dt plus u du by dx plus v du by y plus omega by z. And then 1 over rho, okay, because that's divided by rho, and that is d by dx of tau xx plus d by dy of tau xy plus d by dz of tau xz. Okay, this is just for the x component. You can do the same for the y and the w component. The gi here is 0 because there's only one component, which is in the k direction. Okay, so now remember that you can write u du by dt as d by dt of this. Okay. Square, which is half of twice so that's going to be that term when we multiply by u, and u du by dx is for the same reason. Okay. So when you now do the scalar product of this component with the velocity vector, this, which is this, now you see that we have already a term which is in the form of kinetic energy. And you can write all the stress terms there. And W is the only one which is something different. Now there's an extra term here, which is the gravitational term. case where we have a component for G. Okay, so this is just the scalar product of the momentum equation in the velocity vector. So we have multiplied by u, now we can sum over all the i's if you work in tensor notation. So if you sum over all the i's, what do you get? Just sum over all the i's. Plus the GW. That is going to be equal to U overall of all the stress terms plus V overall of all the stress terms plus W overall of all the stress terms. Now you can write this more succinctly as UI overall UI GI, which is the body force, plus UI so this is the first expression for the conservation of kinetic energy that we have. So this is basically saying that the rate of change of my kinetic energy, we'll define this as kinetic energy, is equal to the body forces acting on the element of fluid plus all the stresses acting on the element of fluid. Yeah? Take the momentum, take the Cauchy equation, multiply by U, multiply by U each component, then you sum over the i's, and you get an expression for the conservation of kinetic energy. Now we can derive from here what is the potential energy in the system. So you can write the body force as the gradient of a scalar potential and we're going to call that scalar potential GZ. Okay, that's going to be my scalar potential, which is just a potential due to gravity. Okay, depending on the height, that's the potential. And so your G is going to be the gradient of that potential. Okay, so my gravity can be represented as the gradient of this potential, and that potential is given by the height. So you can write this UIGI plus minus UI d by dx of GZ, so the gradient of my potential, which is in fact equal to minus the Lagrangian derivative of GZ. And I can write this as the Lagrangian derivative because d by dt is equal to 0, d by dx is equal to 0, d by dy is equal to 0, the only component is d by dz, okay, which is exactly what we have. We can show this. Z Okay, so I'm just working on that. This is equal to 0, this is equal to 0, this is equal to 0. This is minus. This. So that's exactly the term that we had. Okay, so I can express that term, GW, the gravitational body force, as the gradient of my scalar potential. So I say this is my potential, Gz, potential due to gravity, and I can write G as the gradient of that potential. So this term can be written as the gradient of that potential, which I can write as the Lagrangian derivative because it only has one component. Okay, so this is equal to this. And if that's true, then I can put that term into the Lagrangian derivative. Now I can say that the Lagrangian derivative, or the rate of change of energy in my elemental fluid, is the rate of change of the kinetic energy, which is the term that I have here already, plus that term, okay, which is the rate of change of the potential energy. So this term. Now I can write this body force as the Lagrangian derivative of Gz, and so I can put it there. So the rate of change of my total energy, which is kinetic energy plus potential energy, is equal to only that term. Okay, so now I can express the same thing as the conservation of total energy. So the conservation of mechanical energy, kinetic plus potential, is equal to these stresses that are acting on the element of fluid. Okay, so now we're gonna, in order to see all the work that has been done on the element of fluid, we want to look more closely at this term, okay, which is, there's a lot of things into this term, and we can expand that term and see all the different works. There's going to be work due to viscous dissipation, compression, and so on. This is just telling you all the surface forces acting on the element of fluid are going to be equal to my time of rate of my mechanical energy. Okay, so I have that. So this is the velocity times the forces at the surface. But it's not the total rate of work done on the surface. The total rate of work done on the surface is this, which is equal to that one. Plus another term, which is this, okay? So this is now the total work per volume. This is what we had, which is increase in kinetic energy. Okay, so that's the term that we have there. So my kinetic energy, how can it change? The rate of change of my kinetic energy is given by this term. And that term is the term that can make kinetic energy increase. This other term of the total rate of work is the deformation work. Okay, this doesn't accelerate the element. It doesn't increase the kinetic energy, but it can change the internal energy, for example, or it can reduce the kinetic energy by, for example, we'll see dissipation through viscosity. Okay. So this is the total rate of work. This is the total work done on the elemental fluid. So we only had this term so far. So we can rewrite the conservation of energy with the total work and put in these two terms. Okay, so we know that when we have a symmetric tensor times an antisymmetric tensor, that's equal to 0. Okay? The symmetric tensor times an antisymmetric tensor is equal to 0. So the stress tensor tau, this is symmetric, and this other tensor that we know, right, that's the this is the velocity gradient tensor. Okay, this one. This has two components, a symmetric part and an antisymmetric part. It was equal to EJ plus, right, the deformation plus the rotation. This was the symmetric part, and this is the antisymmetric part. Tau ij is a symmetric tensor. So a symmetric tensor times an antisymmetric tensor is equal to 0. So this tau symmetric times the antisymmetric part of this is going to be 0. Okay? So you can write that this is equal to this, because the other component, the rotational part, which is antisymmetric, is going to be V0. Yes.
Excuse me. About that equation, I thought the first term was supposed to be a d squared. Because, for example, if you hold u as a constant, then differentiate the tau, the x.
You're talking about here?
Yes.
So we only have this component, okay, in the equation so far, of my rate of change of energy, mechanical, kinetic plus potential. You have this component. So you have this imbalance of forces. So this is basically telling you that you have some surface forces on the element of fluid, okay, and the net imbalance in the imagine that cube, little cube, okay. So the net imbalance between those forces will give you an acceleration, for example, of the element of fluid, okay. So it might increase the kinetic energy. So if this is not 0, then the rate of change of kinetic energy will change because of this net imbalance in forces. So your rate of change of mechanical energy is going to be equal to all the rate of work done on the element of fluid, not just this term. There are going to be other things happening to the element of fluid that might change the total energy of the system. Okay. So we say that this term is not the total work done on the element of fluid. The total work done on the element of fluid is this, which has two components. Okay. This and this. In 1,000 pieces. No?
Are we getting the terms on the right after differentiating the term on the left? I mean, the second equation, the two terms on the right are given by a differentiation of the term on the left, from the differentiation from the left.
How I get these two terms?
Can
this.
La mancata derivata seconda.
Did I forget anything? Ah, sorry. My mistake, you're right. Now I get it. Now I get it. Thank you. Good. Trying to go fast. I make mistakes. Thank you. So this is the total work done on the element of fluid. Thank you very much. And so you have these two terms, okay? This is the increase in kinetic energy because of the force imbalances in the element of fluid. And this is what we're going to call the deformation work. Okay? And so this term, this is a symmetric tensor, and this tensor has two components. A symmetric and an antisymmetric one. So symmetric times the antisymmetric is equal to 0. And so the only component left is this. So now we know that this deformation work term can be written with this, with the strain rate tensor. So now my rate of change of my total mechanical energy is going to be equal to this, the total rate of change, minus the deformation, which can be written that way, okay? So I'm not going to use this term anymore, I'm going to use the total work done on the element of fluid minus whatever goes into deforming the element of fluid. And now we go back to the constitutive equation for this tau.
Is it minus 1? Not minus?
This is a minus. Okay, is the total minus this component is equal to this. Okay, that was my constitutive equation for the Newtonian fluid. And you can plug that into this term, into the deformation work, so that this term is going to be first term, second term, and the third term. But now we know how to use the Kronecker delta. Okay, that's equal to the divergence of U because of the properties of the Kronecker delta. You can switch the indices. And so this is this plus j minus 2/3 of Okay, so that is the expression for my deformation work. And now I can call all this my viscous terms. Which are all related to the viscosity coefficient, of course. So I have a term on the deformation work, a term which is proportional to pressure, so that's easy to understand. That's going to be effect of pressure on the element of fluid. And these are all terms, so these two terms, we put them together as viscous terms. They're all proportional to the viscosity. So if we go back here, actually I'm going to take out the potential energy. Plus the total deformation minus this, so it's going to be plus this and minus all the viscous terms. So this is the rate of work by the body force, which in this case is changing the potential energy of the system. This is the rate of work by the stresses, tau. This is the rate of work by compression. Okay, you might compress the element, increase its internal energy, for example, or expand it. And this is the rate of work by dissipation. Okay? And it's always negative because it's always a sink of energy, and it's always related to the viscosity, and it's proportional to the square of the velocity. So that term is going to be important in viscous regions, and when you have square the velocity, so usually in boundary layers. So where you have friction with a wall or friction with any boundary. Okay? So that usually takes away energy from your system and usually goes into heat. Okay? So, because I have to go in 10 minutes, I'll just show you basically what we did, and then I'll show you a movie. Okay. Okay, so we multiply the momentum equation by the velocity vector, and we got this expression for the rate of change of the kinetic energy equal to the sum of the rate of work done on the element plus the surface forces related to the tau. Then we worked on this term, okay, which is the velocity times the net force imbalances in your element of fluid or point. And that accelerates the fluid, so increases the kinetic energy, but it's not the total rate of work done on the element of fluid. So you can decompose that term as the total rate of work equal to that term, the term that accelerates and increases the kinetic energy of the fluid, plus a second term, which is not accelerating the element of fluid, but it's a deformation work. So this deformation work can be shown to just have this expression, because the antisymmetric part is equal to 0. Once you multiply that by the stress tensor. And so you end up with the strain rate tensor on the right hand side, tau times the strain rate tensor. You use the constitutive equation in your term, and you arrive to this form for the deformation work. Okay, so basically you have the term that increases your kinetic energy of the system, plus another term which is made of two terms. One is that compression expansion term, proportional to the pressure, and the other one is some viscous terms all grouped together. So your mechanical energy equation can be written from this as this. If you take out from the Lagrangian derivative the potential energy. Okay, so the rate of change of your kinetic energy is equal to the total rate of work done by the body forces plus the rate of work done by the stresses on the element plus compression expansion of the element of fluid minus all the viscous dissipation that are happening in your element of fluid. Okay, so that's how you can describe whatever happens to your kinetic energy in your element of fluid. Same thing that I just said. Rate of work done by expansion and contraction and viscous dissipation. Okay, viscous dissipation usually takes energy into heat, and we'll see the heat equation next time. Those two deformation work terms, one is reversible, the compression and expansion, of course, you can always, that's a reversible conversion from internal energy by the volume changes in the element of fluid, compression and expanding, whereas the viscous dissipation is irreversible. Okay, once you convert your kinetic energy into internal energy or heat, that's totally irreversible. Okay. Your phi viscous dissipation rates is proportional to the viscosity and the square of the velocity gradient. Okay, so it's proportional to viscosity and the square of the velocity gradient. So that's usually important in high shears, wherever you have high shear, so your U square is large and usually goes into heat. We'll see this next time. But see if I can find. I don't know if you know this guy, but he's a famous physics professor of MIT. And he's quite an actor. He puts on some shows on stages.
We will talk exclusively about work and energy. First, let's do one-dimensional case. The work that
Do you know this guy? Have you ever seen
Louis?
Yeah? Lewin.
to the conservation of mechanical energy. I have here a pendulum.
Okay, so the guy just explained the conservation of mechanical energy. Okay, basically what I did. Which has two terms. Okay, kinetic energy and potential energy. So the rate of change of your total mechanical energy is going to be equal to the kinetic energy plus the potential energy. Okay, equal to the increase in kinetic energy due to surface stresses plus compression expansion minus viscous dissipation. Okay, so he will assume that compression and expansion are equal to 0. there is no increase in kinetic energy, hopefully, and there's only going to be a dissipation term. So the rate of change of the total mechanical energy will be equal to 0 or actually diminish. Okay? And he's going to explain that in a very nice way in class.
Object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done. I've increased the potential energy of this object. 15 times 10 is about 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, it's called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you're using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
That was pretty cool, no? Yeah. So, sorry. So, it needed to give 0 speed, so this term was 0. Okay? So, 0 increase in kinetic energy due to surface shear stresses. The rate of work done by compression is nothing. It didn't touch the chin because there were some viscous effects with the air. Right? Yes.
Isn't
Is that a mistake?
yeah?
Yeah.
I don't know. I'm wondering. The first term on the right in the last equation then supposed to be G rho W.
Mm-hmm.
Because if you open up the big D dt of GZ gives us minus GW.
This one,
Yes.
that is supposed to be W.
Yes.
It's in the slide, it's GI.
Well, it's a railroad GW. Okay, sorry, but I have to go.
Physics, laws of circular motion and cheats.
Thank you. I'll see you Wednesday.